Welcome, everyone. My name is Derek Pye, Product Manager for Autoscaling. Thanks for coming to CPN201. More nines for your dimes. Thanks for sticking around this late in the conference. I know I'm between hangover and lunch for you guys, so we'll try to make this interesting and worthwhile. So the topic of the talk today is just about how a few customers like you use autoscaling not only to scale their applications, but also to automate provisioning, improve availability, and save a few bucks. So we've got 4 speakers, 4 customers. You can see who they are right here. So I won't waste too much of your time with a sales pitch. We'll get started with Cameron from the Weather Channel.
Morning, everyone. My name is Cameron-Stokes with the Weather Channel. Before I actually change slides, I have a problem with unexpected weather events. We're pretty good at forecasting. Obviously, most of you probably know us as the Weather Channel. We have our TV station, we have our weather.com website, mobile apps, etc. We're also wonderground.com, or the Weather Underground. And then lesser known are our other companies, WSI and Weather Central, who focus more on business services for the weather. Since we all like to talk numbers, we're a top 30 web property in the US, second most viewed television channel in the US, just behind ESPN. We provide weather forecasting and weather data to 85% of US airlines. We cover about 50,000 flights a day in providing them weather data and forecasts. And we're getting into a space where we are providing weather data to major retailers so that they can forecast their spend and demand and adjust their sales and marketing and so on based on weather. And then we have an unduplicated audience of 163 million visitors across weather.com and the Weather Channel television channel. So before I get to the auto-scaling part, I wanted to touch on how we ended up at AWS, Amazon Web Services, specifically for this application case. So if we roll back about a year ago, it's hurricane season 2012. We're capacity constrained. We have areas of data centers. We have applications that are constrained on capacity, and we're leading up into a busy season for us. So we're looking for options. We're looking to see what we can do to get out of that situation. So we looked around at the applications, and we identified a mobile workload. So a workload that we could easily shift and lift or forklift to a new environment. That ended up being the radar image application for wonderground.com. It was an ideal workload for this scenario. It was a self-contained application, so the website itself was separate from the radar generation, the actual image generation, and it was easy to replicate the data store. So it was very decoupled from any of the other systems within the data centers, within our traditional data center. And easy to pick up and move. So before I get into why autoscaling is a good case for us, who all is using autoscaling in the room? Okay, so maybe a third, right? So for us, we have on a short timeline the typical trending pattern. People wake up in the morning, check the weather before they head out to see what they should wear, see what they're going to do that day. They have lunch, so we get a little dip over lunch, and then into the evening, people stop worrying about the weather so much. Again, this is a pretty typical day-to-day traffic pattern. Works very well for auto-scaling. We can scale up to meet the peaks and scale down in the valleys. On a longer timeline, our traffic pattern may look fairly flat. We have some small blips in there, some small lulls. So over weeks and months, it can still be pretty flat until we get a weather event. And this is where obviously, a storm, something's happening that causes a huge surge in traffic for us. And for us, this was Hurricane Sandy of last year. From one day to the next, this was a 1,000% increase in traffic to our platform. So in moving the application to AWS, we have a pretty basic configuration. We have all of our data is still, the data for this application was still in the traditional data center, so we needed to push that data store out to this new environment. So we have a data bridge, a distribution queue, pushing the data out to data nodes across availability zones. We have the edge nodes or front-end nodes that are actually doing the image processing, so actually building the images, generating the images for the websites, and then an ELB on top of that. So the edge node, the middle tier there is what's actually auto-scaled, and the data node stays static. So this is a chart of out of CloudWatch showing CPU utilization and then host count of this environment. So the top line is CPU, bottom line is host count. And in moving this application out to Amazon, we found that based on the traffic pattern, based on performance profile of the application, that a good band of utilization for us to focus in or aim for was a low of 65% utilization and a high of 80%. We could keep the, at the 65% CPU utilization level, performance was still fine, was still adequate. So we could keep the cluster actually running somewhat hot as we scaled down and save on costs. But if we exceeded 80%, we kind of saw that as our high watermark where we needed to start to scale up. Either performance would start to degrade, or we just knew that the overall scale of the cluster would be constrained. In terms of how we actually scale, we scale up very quickly. So we actually do a percentage-based scaling based on that high threshold of 80%. So if we exceed 80% utilization for a 60-second period, we will actually scale up 20% of the cluster size. So adding a large set of servers into the cluster. If we drop below 65% for a 5-minute period, we will start to scale down in very small steps. So you can see on the chart there those events. And then as we go into later in the day, you can see it'll actually scale back up again. So that actually works really well for us. Again, we really honed in on that utilization range. We get good performance of the application, so response time is still very good for our end users, and that really gives us a good kind of price point to focus on in terms of CPU usage for the cluster. But we do have some challenges, and you probably will too. So first off, your monitoring tools probably suck. And they probably suck for a traditional kind of static environment, and they're really going to suck in a dynamic environment. As nodes, as hosts, come up dynamically, as they are removed dynamically, that's challenging for most monitoring tools to really either do host registration or track metrics, add alerts, add alarms, and so on for all those dynamic hosts. So leverage CloudWatch as much as you can, and look for modern monitoring tools that can adapt to a dynamic environment. Rolling out application updates is a bit cumbersome. There's a lot of moving pieces to auto-scaling. There's groups, launch configurations, alarms, policies, and so on. Launch configurations are where you actually define your application data. So you define your machine image, user data, tags, et cetera. To roll out a new version, you create a new launch configuration with your new machine image and those other config points. But actually changing that, creating a new launch configuration, changing that onto your auto-scaling group doesn't actually change your environment. There's no kickoff of rolling out your update automatically. So a couple different options. You can basically wait for auto-scaling to happen and roll in new instances with the new launch configurations and roll out the old ones. That's a policy that can actually, or a strategy that can actually be tweaked within auto-scaling. Or you can actually intentionally go in and roll out or remove old instances yourself. That's the strategy that we're currently doing. So as we create a version 4.1 of our launch config, we would actually go out and just one by one kill off the old instances. Another strategy or another option that we're looking at is actually standing up in a completely new auto-scaling group with that new configuration, scaling it up to the current capacity of the old group, and then shutting down the old group. We haven't quite gotten there yet. This isn't so cumbersome that we've had to put the effort into that, but that's the direction we're going to be heading. So this isn't necessarily an auto-scaling issue, but it is auto-scaling again puts some burden on you in managing this cluster, managing your fleet across an auto-scaling group. So for us, when a zone failure happens, and it's not necessarily Amazon having an issue, but it could be our data node having an issue, we get to this, we basically cascade that failure into our other zones. As one zone is essentially dead, traffic will redistribute across the other ones and then takes those down with them. That's really where getting that CPU utilization, getting your policies, getting your min and max and desired capacities right is really key. Making sure that you have over-provisioned capacity in the other zones to make sure that if that failover happens, you're not taking down those other zones as a result. And then lastly, there are lots of knobs and switches to get right or wrong. I mentioned auto-scaling groups, launch configurations, alarms, policies. Each of those has many different settings, many different configuration options on themselves, or on those. Getting the right mix of those for your application, for your performance profile that you're expecting, for a good user experience for your application is difficult. It takes a lot of changes. It takes a lot of iterations to really get that right. You will not get it right the first time. Plan to set it up, test it, try it, and then make tweaks along the way. So with that, I will turn it over to Keith.
Hi there, I'm Keith Baker from Nokia, and also I'm in the mapping side, so here.com you'll see mentioned as well. And it's just the group that I'm in. So I'm going to talk about using auto-scaling for some things that people don't necessarily think of as auto-scaling, because scaling isn't really part of it. In particular, we use it to maintain a non-critical application. And this is our Clickwork Annotation application. So it's used internally. It was our first step into Amazon. We have about 100 users. They're all hourly contractors. Downtime is actually sort of acceptable. We don't want to, really take people off by sort of, they can't get their work done. But at the same time, it's not, customer facing. We're paying them to be there. So we sort of have a captive audience. We can let things happen. We ported it from an internal application, and our goal was actually to get better uptime, because we had some problems in our traditional data center. But it sort of gave us a really good way to start off in Amazon. This is the basic architecture of the site. It's a single instance running a Django web app with a Postgres database on it. It's backed by it has two ABS volumes that are actually in RAID 1. We download configuration out of S3. We push backups of the database into S3, and we also do snapshots. We have a single ELB out front doing SSL for us, and Route 53 for the names. We use a little bit of CloudWatch just to, if the instance is down for longer than we expect it to be down, it'll notify us. So as I mentioned, single instance, single AZ, auto-scaling set to maintain one instance. So if it goes down, a failure takes about 15 minutes for it to come back up usually. Usually is sort of a bit unfair to Amazon. It actually doesn't fail that often. The most common reason that it goes down for any length of time is actually upgrading it. So upgrades are done with planned downtime. We tell people it's going to happen a week before, and then we just run a redeployment. In general, that takes the same 15 minutes. Sometimes we have a database schema update while we're doing the update, and that actually executes before the site goes live again. So sometimes it's a little bit longer if we have to do a major update. Those are pretty few and far between, though. Oh, I should mention there, we also use the snapshots to test the upgrade and the database schema change beforehand. So we'll just take snapshots of the EBS volumes and then spin up a different test node and make sure it runs perfectly before we do it. It gives us a very, basically the database we're going to do it on in production is very similar. So that's helped us actually a lot with those updates. So while the uptime is flexible, our data is actually really precious. We're paying people hourly to make this data. We use 2 EBS volumes in RAID 1. So we have a copy there. That's mostly for trying to keep it up. We'll get an alarm if one of the EBS volumes goes bad. It's never actually happened. The only time things have gone bad is when they've all gone bad. We have periodic backups of Postgres. We just do PG dumps. We encrypt them and stick them in S3. We used to do it daily. We actually increased it to hourly because we ran into 2 of the EBS outages. We must have really picked the wrong availability zone. We got 2 EBS outages that took us down for sort of 11 hours, and we wished we had had the backups. We ended up getting all of our data back because it just came back, but we actually at one point had thought about moving it to another availability zone and bringing it back up off of the backups, but we were going to lose 5 hours worth of work, so we decided not to. 5 hours worth of work by however many taggers were working, which I think was around 10. So we have the EBS snapshots. They're manual right now. We usually use them for the testing upgrades, but we can also go back to them if we needed to. In general, our backup is really the Postgres dump. So using auto-scaling, the one thing that really has to be true is the system can't be configured by hand. It actually has to recover itself. So what we do is we use masterless Puppet. Basically, we build a Puppet tree into an RPM, stick it in S3, and then we use Cloud Init to configure that repository, install that Puppet configuration from the RPM, and then kick off a Puppet run. Puppet installs all the needed packages, actually connects the EBS volumes. At that point, I don't think I knew about mappings for instances, so I didn't actually have that. The Puppet code just calls the Java tools to mount the EBS volumes. It then configures the RAID, starts Postgres and Apache, and your instance is back up and running. We could have done this as sort of building an instance and then snapshotting an AMI and then letting it sort of reboot itself on that AMI. We wanted all of our configuration stored in our source repository. So we can sort of build this from a CentOS AMI plus Cloud Init, and then everything else is all in our repository. So we can go back to 0, and it's not in someone's head how it was configured. We could, at this point, take an AMI of the configured machine, but it happens so quickly we don't bother compared to the time the instance takes to just, auto-scaling has to notice that it's down, and then it has to create a replacement, and this is 2 minutes or something added to it because Puppet has to do more work than if it was just a disk image. So in terms of Clickwork, it was totally successful. We moved it to Amazon. We drastically increased our uptime over the server in a closet. We had 2-day outages, actually, for a hurricane. We lost power to our data center, which was, I'll use data center. So moving to Amazon basically got us much better uptime, which is good. I mean, as I said, we didn't really need it, but not making our workers miss time was a good thing. We designed for one-day outages. We've had 2 outages in the past year and a little more. Sorry, actually, almost 2 years. They were 2 hours and 9 hours. They were both EBS-related events. We could have designed this to avoid the EBS events. We just didn't, we didn't need to. We didn't need to spend the cost. And it was sort of known. We were prepared for that. So that got us past the sort of first deployment. We got through all the bureaucratic hurdles. We're a big company. Amazon, it's public cloud. And then so we got to something more fun. We got to actually move our local search application. It was our first customer-facing application. Obviously, it needed to have really good uptime. We provide the one-box search for here.com and also for all Nokia phones, or really any Windows phone that you load the here.com app on. Our architecture here, we deploy to 4 regions currently. We also deploy to multiple AZs, and then we use an ELB between the AZs. And depending on the region, depends on how many AZs we do. Interestingly, sort of going back to the whole single node, we do a lot of single node autoscaling groups. So instances with one node in those clusters automatically register themselves in DNS with Route 53 based on an autoscaling group name. So when you reboot a node, when a node dies, it will re-register itself with DNS. The autoscaling group names and DNS names are formed with a pattern based on the cluster name. So cluster 1 front ends can find cluster 1 zookeepers, cluster 2 zookeeper, et cetera. So we could have done some API queries with the autoscaling groups, but we decided to use DNS because it sort of allowed us to use a whole bunch of standard tools that just look for a server via DNS name. You have to be a little bit careful of what tool you're using, and I'll get into that in a second. So one of our primary uses for this is Zookeeper. We have 3 single instance autoscaling groups. Each one maintains 1 Zookeeper server. And the reason for this is that Zookeeper actually needs a consistent set of servers across all nodes. If you do an autoscaling group, you don't have necessarily a way to order them. So we just did Zookeeper 1, 2, and 3, and they all maintain themselves. If one goes away, it starts back up, rejoins the group, and gets an update, and then is usually happy. So when we launched, and I think this has been fixed now, but Zookeeper didn't re-resolve host names on the server. So you couldn't just say, Zookeeper 1, Zookeeper 2, Zookeeper 3. We actually used inetd and netcat to just, Zookeeper would connect to localhost, which would be the inetd, and that would start up a netcat, which would look up the host name and connect. So you basically get a DNS lookup on every connection to the server. This actually has worked really well for us. They tend to not have problems with it. We end up not having to use elastic IPs. You could use elastic IPs if you wanted, but we figured why not just use DNS. It's sort of a long-proven technology. So the clients, thankfully, had been fixed. We didn't actually have to do any trickery with the clients. We just told all of our clients that use Zookeeper connect to that name, and they're fine. You do have to make sure that Java isn't caching the DNS lookups. It is a lot better than it used to be about that now, but it will, in some modes, it will cache host names forever once it's looked them up. We also have to keep our DNS timeouts pretty short, but only internal things are looking these up, so it's not like we're hammering on DNS servers. But if your TTL is too long, right, it's going to take a while for the node to come up, change the host name, and you're going to have to wait a while until that host name necessarily is flushed out of caches. We considered doing a zookeeper per AZ, but some of the regions we deploy in only have 2 AZs, and if one AZ were to fail, we might lose quorum, and then both AZs would be down. So we're using 3 zookeepers and 1 AZ in a cluster, and we have lost them all at once. They go offline, and the node, our cluster detects that it no longer has zookeeper and goes unhealthy in the ELB. The ELB goes offline, and things keep working. Zookeepers come back up. We importantly don't have locking in zookeeper, so they can just re-register and they can find each other again. There's no actual state that we really care about there. So logging, we do the same thing with logging. We have 1 logging node that basically buffers log for the entire cluster. Each host pushing to that log node also has a capability to buffer, just in case this 1 log node dies. It just gives us a place to do compression, encryption, and periodic uploads to S3 without affecting the performance of the other nodes. So if it goes offline for a little while, we don't actually care. It also, in our case, forwards to a central logging system for the rest of the company. But it does provide us a single point of investigation for the entire cluster. We tag all incoming requests with an ID, and then that gets propagated to all the sub-requests that we do to get data back. And we can just grep for that ID across that 1 node, and we'll find all of the sub-queries that were created. Yeah, I mentioned all scribe nodes. So updating, we update data on these nodes. We used to have it so that every one of the nodes would sequentially go offline, update its data, and then come back online. The problem is that as your clusters get bigger and bigger, that takes a really long time to update all your data. So we're moving to a system that will basically take a lock in zookeeper, and then when the cluster size, it will increase the cluster size, and then that new node will get new data, and then all the nodes will get updated at the same time, and they can kill. They basically, once they see that the one they spun up has updated its data, it can kill itself off, and then everything's updated. You have to be careful sort of with tracking to make sure that the node that spins up a node waits for that one to finish, and they sort of have to coordinate with that. We're using the auto-scaling messages to keep track of that. So we've been really successful. All of our detected health problems have been successfully replaced with auto-scaling with no intervention. We've been paranoid, so it still pages us, but it's sort of beginning to feel silly. The zookeeper setup has worked great for us. Our biggest problem has actually been undetected problems. Disk failures and intermittent connectivity failures have been our highest problems. The disk failures are something that I expected when Amazon says sort of designed for failure. I thought they'd notice those and terminate nodes as being unhealthy. But when you really think about it, if you look at like the 24 disk instances, one disk going bad is not something that your application may be tolerant of that. So we actually wrote code to look for disk errors and terminate the instance. And with that, I'll hand it to Laurent from Adobe.
Thanks. Hello, everyone. My name is Laurent, and I'm with Adobe. And I work in a team called CloudOps. And what we do is we provide technical operation services on behalf of our internal clients, which are our internal team within the company. Adobe is moving pretty aggressively to the cloud. The Creative Cloud initiative, which is an initiative that started about 2+ years ago, was designed from scratch to run in Amazon. It was also designed with a back-end common platform, where the idea was to be able to reuse that if other internal teams within the company wanted to build additional products. And so what I'm going to be talking about today is how we use auto-scaling on this common platform. We call that the shared cloud. So before I get into autoscaling, I thought it would be important to recap a little bit what the goals are when you want to use autoscalings and what it meant for us. And for us, it meant really three things. One was to meet demand. Well, that's pretty obvious. You never want to be in a situation where you don't have enough capacity to meet your user demands. But the other thing is we wanted to control costs. This is the cloud. It's a pay-as-you-go model. If you allocate resources and you don't use them, it's not like you can go back to Amazon and tell them, hey, I didn't use my resources. Can you give me the money back? Probably not going to work. I haven't tried it, but. The other thing is we wanted to use autoscaling to maintain capacity. And what that means is you hear everywhere that EC2 is an ephemeral service that instances can disappear into thin air at any given notice. That really never happened to me. But EC2 instances can go berserk, and more likely because of the software that you install on it. And so what we did is we actually took advantage of that and created one of our most useful standard operating procedure, which is that if it doesn't work, just kill it. And I learned this week that there's a term for that. If you attended Christmas session on Wednesday, he calls that stone it. So our operations team knows how to do that. The instance is not behaving properly, they just go ahead and kill it. And we also built some automation with our monitoring tool to terminate misbehaving instances and then rely on autoscaling to bring capacity back up. Okay, so quickly, the architecture of the shared cloud. It's a fairly simple distributed asynchronous architecture. You got a layer of web servers that take requests behind an ELB. A lot of the business logic is then delegated to a worker layer via SQS. So the web layers post jobs to SQS. A worker layers consume those jobs and do some processing and then publish the results back into another queue. And the worker layer is actually something that we have today 30 workers. Our engineering team is pretty smart. They created an SDK that allows other teams within the company to create new workers. So the number of workers is actually growing pretty quickly. An example of workers would be some transcoding activities or metadata extractions or thumbnailings and things like that. And so what I'm going to be talking about today is how did we scale the web layer and how we scaled the worker layer. So on the web layer, well, when the web components came to us, they were actually rated. Engineering team told us, hey, we tested this thing. They can handle 900 requests per second. So right on, that was good. We definitely used that metric right away to be able to scale on that. But we pretty quickly realized that this wasn't enough. Not all requests are the same. Some requests are slower. Some requests are faster. Some requests take more CPU than others. And some requests use a lot more network bandwidth than others. Right? If you upload a gigantic video file, there's going to be a lot of inbound bandwidth that's going to be used versus if you make a request for some metadata, which is just a very small amount of information that would be outbound. So what we did is we added additional metrics and additional policies to be able to scale on those conditions. So the good news is those metrics are readily available in CloudWatch. CloudWatch provides aggregated CPU across your scaling groups, aggregated networks numbers across your scaling groups. They're not always usable directly. And I'll touch a little bit on that, on how we overcome that problem and what we did. On the worker layer, as you saw, it's all based on SQS queues, so that was pretty easy. We basically scale based on the number of messages that have not been consumed in the queue. We tried to look at other ways to scale, like, for instance, CPU. For us, it didn't work because those workers, they are configured to only handle a fixed number of jobs at the same time. So, you know, the CPU is probably going to stay static no matter how many messages are waiting in the queue. So it doesn't really tell us how busy those systems were. So right now, we only have one scaling metric that we can use for that layer. So that's great. We know how to scale up. This is good. But how do you scale down? Well, it turns out scaling down became a little more of a headache than what we anticipated. There's a little bit of a fear factor here. Right? What if you scale down in the middle of the day, and then all of a sudden you have this surge of requests, and you remove your capacity? And then the other thing is scaling down is not always very graceful. So I don't know if you had experience with scaling down instances that are behind ELBs. Basically, the deregistration is pretty abrupt. All the active connections are dropped, and the instance is removed. And then on that worker layer, we have some workers that take a bit of time to process. We have some conversions to PDF, for instance, that could take minutes. If the instance where the worker is running on is selected for termination, that job would just never complete. The data is now lost. Job goes back in the queue, and your worker is going to pick it up. But while we use an asynchronous process, we still want those jobs to be processed pretty fast. So what we did is we actually went live with no downscaling. And we made the conscious decision to do that because we wanted to learn about what our pattern was so that we could make a conscious decision on what numbers to use and what metrics to use as well. OK. So, but if you want to do cost control, then obviously you're going to have to do downscaling. So after we analyzed our traffic when we went live, we went back and looked at our scaling history and also our usage. Well, we learned that our pattern was pretty typical of normal usage. People are starting to use the product in the morning, and there's a ramp down in the evening. So that led itself to allow us to put together some schedule scaling, right? Just scale up in the morning and then scale down in the evening. The other nice thing about this is that you can be proactive in terms of having the capacity that you need right away. One of the issues that we have with scaling is we never scale fast enough. Right? If you have a sudden spike, it will take some minutes, some amount of time for instances to come up and be configured properly before they become actually useful. And so schedule scaling allows us to put some capacity ahead of time. And then in the evening, we just scale down because we know that there's going to be less people using the product during the evening and the night. And because we have auto-scaling, if there was some people that would all of a sudden use our products in the middle of the night, then auto-scaling would take care of that. Once we learned about our pattern as well, it allows us to create some more policies to scale down. And what the important part here, the important thing here is that you want to scale down very slowly. Like if there's one thing you want to remember from this session is you want to scale up very fast, but you want to scale down very slowly. The other thing that our team does is we manage the stage environments. And so those stage environments are used by various teams to do integration testing and load testing and all kind of other testing. And the usage is not predictable at all. And so what we decided, but it still costs money, right? Amazon doesn't differentiate between dev and stage and production. It's all the same stuff. And so what we did here is we took an aggressive approach to basically downscale everything to the minimum size every day. I think we do that multiple times a day now. So we have some cron jobs that just go ahead and downscale the environments quickly. OK, so you're going to ask me, how do we do this? Well, we firmly believe in CloudFormation. We use CloudFormation extensively across all those workers and web layers. Each worker has its own CloudFormation stack. There's a colleague of mine, actually, that presented the way that we do deployments at Adobe for this service. We do A/B deployments, so meaning that if you have an A side that is active, then in the background we build a B sides that we test, and then when it becomes it's test and pass all the criteria for release, then we move that into to be in production. So what I'm trying to show here is that it's not how to use CloudFormation, but just how easy it is to put a policy and an alarm in your template. It's a few lines of code. Here it's scaling based on the SQ. And because for us, we're still using CloudFormation, was the right way to go. But what if CloudFormation doesn't support what you need? For instance, so auto-scaling supports natively schedule scaling. But you can't really set that up with CloudFormation today. So what we did here is we created some custom scripts to perform those scaling in the morning. So we have some basically predefined configuration settings. Scale this worker to this number of instances in the morning, and then scale to this number of instances in the evening, business hours or weekend hours, for instance. So this just simply run as a cron, look at all the auto-scaling groups that we have, and then scale them down. So this is the output of the log. It's actually a very simple script. The other thing is, I mentioned earlier, CloudWatch has a lot of metrics, but for us, they were not necessarily usable directly. So for instance, the number of requests coming through the ELB. Well, that's a very good number to know, but it's not very good for scaling because it doesn't take into account your current capacity. And what that means is that when you reach a certain threshold and you scale either up or down, you would have to change that number. And so that means updating the alarm every time there's a scaling event. So what we did is we actually consumed those CloudWatch metrics, but rewrite them as custom metrics that make sense to us. In this case, the number of requests coming to one instance. And that's great. If you reach a certain number and you add some capacity, then the alarm will clear, and then you don't have to change anything else. And so we do that on our web layer for number of requests, and then also the CPU, the aggregate CPU across the scaling group and the network bandwidth. Okay. So the other thing that we realize is not all spikes are the same, right? You got the very slow ramp up, you have medium ramp up, you have very sudden ramp up. And the way auto-scaling works today is that it's basically one policy, one metric. And so if we take the example of a worker where there's a few messages in the queue that needs to be processed, then you may want to add 1 or 2 instances. But what if there's 1 million messages to be processed? 1 or 2 instances is just not going to cut it. You want to add a bazillion instances. And so what we did is we have this tiered level, what we called, for better or for worse, multi-input scalings, which basically scale more or less aggressively depending on the criteria. And this is not perfect, right? If you look at the scale up, like condition number 3, if condition number 3 is true, right? If you have adding a fixed number of instances, you have more than 10,000 messages in the queue for more than 1 minute. If that condition is true, then condition number 2 is true, then condition number 1 is true. And so what happens, right? Well, all those policies may be executed randomly. And so what's important to do here is to try to leverage this to, first of all, not have too many of those so that you have more chances to use the right policy. And then the other thing would be to take advantage of the cool down periods that you can set, because that will allow you to run those policies at different times. So if I have an advice, this is my last slide, use CloudFormation. I know there's a lot of people using CloudFormation. There's a lot of people not using CloudFormation. If you've done auto-scaling without CloudFormation, you probably know how much of a pain it is. There's a lot, you got to create launch configs, you got to create alarms, you got to create policies, you got to create scaling groups. So use CloudFormation. The other thing is know your system. This is how you're going to know what kind of metrics you're going to be able to use. How you're going to scale. What kind of policies do you have to put together? What's your scaling history? Amazon provides an API to describe all the history. Just use it. It's there for a reason. And that's more experience. Scaling up is easy. Scaling down was not so much easy for us. And it might not be the case for you, but just remember that this is not an easy thing to do. And then the other thing, like I said, to remember, scale up fast and scale down slow. And so with that, I'm going to hand it off to Brandon. Thank you.
Hi. So I'm Brandon Adams, and I'm from a company called Dreambox Learning. So I'm going to tell you today about how to scale with CloudWatch alarms and how to use performance tests to accurately find the points that you need to scale at, how to use scheduled scaling, and how to scale with multiple CloudWatch alarm conditions. So a little about us. We're a Rails app. We use the Unicorn app servers, and we teach kids math. So what our product does is it figures out what kids need to learn and adapts to their needs. So because we're in education, we have a workload that's really well suited to auto-scaling. This is a graph for a typical week for us. You can see we scale up in a big way right in the middle of the day, but for most of the time, we don't have all that much traffic outside of those periods. On the weekend, we've got a little bump, but At night, almost nothing because those kids are asleep. So scaling with CloudWatch alarms. What's an alarm? It measures some metric in CloudWatch. Go above or beyond the threshold, an alarm fires, and that could be used to trigger an auto-scaling action. So before we get to creating our alarms, we need a performance test to figure out how much load our app servers can handle. We need to discover the ideal number of worker processes that we can use on our servers, because if we go too few, we're wasting resources. If we go too many, we've got resource contention, and that's going to cause our performance to suffer. We need to figure out the maximum load that we can sustain per server, and we need to find the metric that we need to scale on. For us, this is CPU utilization. For you, it could be something different. So this is a typical perf test for us. We use New Relic to monitor our application, and you can see the perf test moseys right along, and performance is great until we hit a point, and suddenly we go really bad. So we want to tune ourselves so that we scale up before that happens. So we identify the breaking point, and then we correlate in time with our CloudWatch metrics and find out how much CPU we are using per instance at that breaking point. You can see it's about 80% TPU there when we went off the rails. And our performance test framework will also tell us how many concurrent users we had. This happened at about 400 users per server. It doesn't produce graphs, but it has text output that tells us that. Our first method after obtaining this perf test data was to just guess and check. We provisioned a static set of servers that we knew could handle the load based on the numbers that were revealed to us in the perf test. And then we started to just scale up and down very conservatively. So we'd scale up at like 35% CPU because we wanted to make really sure that we didn't run ourselves off the ground. And this worked. We were able to find the scaling points, but it was really inefficient because we were over-provisioned while we were figuring out where we needed to scale. And it took us a lot of time to dial that in. So we thought we could find a better way by doing math. So for doing math, we want to identify the variables that are involved. For us, the independent variable in the equation is concurrent users. There are a number of dependent variables that a spike up or down in concurrent users can affect. CPU utilization, memory utilization, disk I/O, network I/O. For us, it's CPU. And so after establishing that, we can do some math. So this graph right here is a graph of our concurrent users over time. And this is about an hour. And you can see I drew a slope line, and it's about 1,600 users per hour that we're adding at this point on our graph. It's about 27 per minute. We know from our previous test that we can handle about 400 users per server. And when we're at that point, we're at about 80% CPU usage, which is about 0.2% CPU usage per server per user. And we know from our other testing that it takes us about 5 minutes for a new node to come online. We're adding about 27 users per minute. So at the bare minimum, we need to start spinning up new nodes when we're about 135 users per node short of that max, which is about 53% utilization. So we've got an equation right there. It's a little messy, but I've got it more formally stated on the next slide. So you can see our scaling point is the maximum users per node minus the users that we're adding per minute times spin up time. Follow the equation. You see it works out to 265 users per node. And then on the bottom, you can see we've got scaling point users per node times CPU per user. Works out to about 53% CPU per node. And from my physics undergrad courses, I know that if you take care of the units, they'll take care of you. And so you can see we cross out the units, and our units match up. The units on one side of the equation match the units that result on the other side of the equation. So how much do we need to scale up by? For us, the lowest we can scale up by is 1 node per AZ, because otherwise we'd be unbalanced, and some of our AZs would get more traffic than the others. That's just how BLBs work. At least it used to. They introduced a new feature that fixes that. For us, when we add 1 node per AZ, we're in 2 AZs. This is an extra 800 users of capacity, and we're doing that in 5 minutes. So that would be plenty enough to keep up with that curve, which is 1,600 users per hour. If we're adding 800 users of capacity every 5 minutes, we don't need to worry about bumping up how many nodes we're adding until we hit 9,600 additional users per hour. So we've got these predictions from our perf test framework. Let's evaluate them. In the real world, we actually scale up a little bit higher than 53% because our perf test framework is a little harsher on our servers than the real world, which is a good thing. Otherwise, we might start at a level where we'd have performance problems. Yeah, and you can see this is a graph of node count plotted against CPU. And so you can see the spike ups happen a little bit after the 53% level. So next up is scheduled scaling. We scheduled scale because the acceleration in our load is not constant. I drew some lines through some of the more linear areas in the graph. And you can see the slope is wildly different between the three, which means we can't use a single rule to capture all the scaling that we need to do. If we used a rule that was too aggressive in scaling up, we'd end up over-provisioning, and we'd have bounciness. That's when you scale down and then you scale up before an hour is up, which results in extra charges for you because Amazon bills by the hour. So if you get rid of a node and then bring up a node to replace it less than an hour later, you're paying twice for it. If we scaled too timidly, we'd have poor performance and we'd have outages because we'd lack the capacity to serve demand. So to take care of that, we add scheduled scaling points to eliminate the bounciness. We scheduled scale for those steepest parts of the curve that I showed earlier. And we let dynamic scaling take care of the less steep parts of the curve. And as serendipity would have it, while I was making this presentation, I found a bouncy point. So you can see it's highlighted on the graph there on the far right. We scale down, and then less than an hour later, we scale right back up again. We're scaling down too quickly there. And you can see on the graph, I've identified our scaling points. So at each scaling point, we set a new minimum for the auto-scaling group. And you can see that we've set our minimum a little early of where we need to set it. So I corrected that problem, and then here's the graph for the next day. We moved our minimum out, our scheduled scaling minimum, and we eliminated that bouncy point, saved a few bucks. Lastly, I'm going to show you how to scale with multiple CloudWatch alarm conditions. So why would you want to do this? Every now and then, maybe like 3 to 4 times a month, we'll get an unexpected spike in traffic that we can't predict based on past trends. And it's at a high enough level that performance suffers, and if it's really high, we're going to have an outage because we don't have the capacity to serve demand. We thought we could just fix this by adding another alarm. Say, like, we're scaling up to 65%. We'll add another alarm at 80% to scale up in a really big way. But that's problematic because there's no way to choose which alarm triggers when both conditions are met. And your low scaling point alarm could end up squishing your high scaling point alarm and stealing the action that it wants to take. There's a cooldown period, and so as long as the cooldown period is in effect, your other alarms can't fire and can't cause you to take auto-scaling actions. So our solution was to have multiple auto-scaling groups. So you have multiple auto-scaling groups with multiple alarms. We apply that high demand alarm to just a single auto-scaling group. That high demand group normally has no instances in it. If we reach that high demand threshold, we scale up that group that normally has 0 instances. And we know it's going to scale up because the alarm only applies to that group and there's no cooldown period in effect. And that saves us from performance problems and outages about 3 to 4 times a month. So it's significant. So putting all these together, you end up with a demand curve that hugs your usage curve. So this graph right here is our provision node count versus our concurrent user count. And you can see they're fairly coincident, and that's a result of the scaling strategies that we put in place. And you also get a mostly flat response curve. This is another snapshot from New Relic. This is over a week's time. It would be a little flatter, but you can see on the left there, I don't know if you can read the dates from where you are. That's Halloween, so I don't think many kids were playing on Halloween night, so we had less demand. All right, that's it. Thank you.